Hello, this is Changyer Kim, and this presentation is about post-processing for individual fairness paper review, and the author is Felix Peterson. First, I gonna talk about other post-processing formulation and why this paper suggests post-processing algorithm to enforce individual fairness. Then, I will tell about background information and what this paper assumes about the learner. Third, I will shortly say about the works algorithms problem. Then say about graph smoothing problem, that is this paper's algorithm. And next, prove local individual fairness of this algorithm. Lastly, review experiment of this paper. There are three kinds of post-processing formulation. First formulation is used in processing algorithm to reduce algorithmic bias. But it has same problem as in processing algorithm, that it is most demanding in terms of input, like original model's input or how predictor looks like or other function used in model, and needs some computational requirements for retraining too. Second formulation is train additional model to correct initial model. And it assumes that we can train weak learners to boost, but boosting is not can be applied to our situation, so it can be a problem of second method. And third formulation is post-processing with only access to original model's output and feedback guiding fairness constraints. And this method is most general, and there are algorithms that satisfies group fairness, but it is not applicable to individual fairness. So, based on third method, uh, this paper proposed post-processing method that enforces individual fairness. The name is Global Laplacian Individual Fairness, short as GLIF. The background information. Post-processing is correcting bias in machine learning systems that are already used in production. And I said before that there are several methods like in-processing or post-processing and pre-processing. And the advantage of post-processing is because it does something after training, so it can avoid expensive retraining. Individual fairness is treating similar individuals similarly. That means if A and B has similar property, results should be also similar. And even if on similar individuals, um, the difference between output must be bounded. And mathematical definition of individual fairness is equation 1 here. And parameter of equation 1, I will explain it. And dx and dy is fair metric that represent fair distance. H is objective function, and x prime is individuals of individuals. We can say that input of post processing. Equation 1 says distance of output is smaller than distance of input multiplied by L. By changing equation 1 to equation 2, we can see that individual fairness means exists a boundary in gradient of objective function. And this paper assumes that we have access to prediction and similarity graph. For example, there are prediction as left, A0, B1, C1, and similarity graph as center that represents similar individual as thick arrow, and this similarity graph represent A and C is similar. So we can make adjacency matrix with similarity graph like right table. Actually, D-Works algorithms are also proposed to enforce individual fairness with post-processing, and D-Works algorithm objective function is like this. F is objective function and n is individual dimension, and y hat is output of original model, and dy dx is parametric that I said before. And this function minimizes that objective functions result and original results fair distance become minimized. Objective function is a function that modify original model's output to post-processed output. And first line equation shows that I said before, minimizing the difference between post-processing and original output. And second line of equation shows that it applies individual fairness. This is directly individual fairness equation. However, this paper says D-Works algorithm leads output dissimilar to actual result, and this algorithm has two problems. First, empirically, D-Works algorithm has bad trade-off with accuracy because it restricts individual fairness in global region. As we see in equation here, we doesn't specify the xi and xj's region. Yeah, so it is one problem, and also it has poor scalability because it needs much more time when dimension of y increase. Then I will talk about this algorithm's main background information, that is graph smoothing problem. And smoothing means that modifying data to reduce individual points higher than the adjacent points. It usually used in remove noise in image processing, and remove noise is also kind of applying individual fairness because points that have noise will be not similar to adjacent point. In this paper, graph smoothing means reduce difference between similar individuals with similarity graph, and it is same meaning as make output individually fair. To graph smoothing, this paper select objective function that satisfy equation 1. Lambda is penalty parameter and Ln is graph Laplacian matrix. First box make objective function occur as original output, and second box make objective function individually fair. I will say the reason later, and by setting gradient of equation 1, objective function is easily derived as equation 2 here. And if we assume graph Laplacian matrix is function of adjacency matrix as equation 3, equation 4 says that to minimize F transpose LF, then Fi and Fj will become small when when Wij is 1, that means I and j is similar. So we can see this objective function will be locally individually fair. This will be proved later. Before proving local individual fairness, let me simply introduce advantage of this objective function compared to D-Works objective function. That is, it is easy to extend dimension, and uh, as as this equation shows, only thing to extend dimension is change two norms in equation to Fourier norm here and here. So this algorithm can be used widely and commonly. Now I will begin proof of local individual fairness of GRIF. The definition of local individual fairness is that we say H is locally individually fair if equation 1 is satisfied. Equation 1 is this equation, and the difference in term local is while individual fairness must satisfy equation in whole region of x comma x prime. That means like this. There are no specified x comma x prime region, but in here there are some specified x comma x prime region, that is parametrics between x comma x prime is smaller than epsilon. Let's assume parametrics as following equation, like this and this. Dx is actually Mahalanobis distance and dy is Euclidean distance. By using Lagrange mean value theorem, below equation easily derived. Lagrange mean value theorem is this one. You can see it, you learn at middle school or high school, and this equation is just applying f as h, and f prime c is gradient of hx, and this sigma comes from here Mahalanobis this sigma. And this means locally individual fairness can easily satisfy when gradient hx is not infinity. When this is not infinity, the whole of this will be smaller than not infinity. Thus, gradient hx will be infinity only when it is this continuous function. So it will not be infinity when w is continuous. And when we assume adjacency matrix as following equation, we can derive equation that below equations that satisfies local individual fairness, and this adjacency matrix is for unnormalized adjacency matrix. Ignore this term and actually this term too. 2 sigma 1 over 2 sigma square, and the d is dimension of input and sigma is standard deviation of individuals. To prove local individual fairness, we will prove that gradient of parametrics is not infinity. So by assuming mean and max value of probability exists, that is p mean and p max, and objective function and probability function are bounded, and its derivative function also bounded too for I, and I is 0, 1, 2. Below equation shows that it also satisfies local individual fairness, because this must be not infinity when this and this not be infinity when this assuming with this assuming. And then I will tell about experiment of this paper. And first experiment is comparing accuracy and individual fairness after post-processing by GRIF, that is graph Laplacian individual fairness, GRIF NRW, that is GRIF normalized random walk, and global global IF constraint that is as we know as the works algorithm. This model is classifying words as having positive or negative sentiment. Actually, it is grading a sentiment of words. There are word name pair, and this model output shows that there are different sentiments to a name and has different average sentiment between Caucasian and African American likely name group too. Accuracy evaluated by difference between original output, and fairness evaluated by comparing prediction on name and check accuracy fairness trade-off by changing tau and Lipschitz constants. Tau is the parameter that defines which Mahalanobis distance become similar individuals, that is meaning local individual region, and Lipschitz constant is boundary of local individual fairness. The result of experiment 1 is first, to calculating objective function, IF constraints need 7 minutes while GRIF needs only 0.1 seconds. Second, GRIF has always lower standard of sentiment by name, that means more individually fair for the same accuracy. Also, has smaller race gap between Caucasian and African American group. At below graph, blue line is IF constraint and red line is GRIF and green line is GRIF normalized. Left graph represents sentiment by name and right graph represents sentiment by race group. Sentiment by names data has more bias in high density region than sentiment by race group. By comparing left and right graphs GRIF, difference in normalized unnormalized GRIF is that unnormalized GRIF is more accurate in high density region, that is left graph, and less accurate in low density region. And actually normalized Laplacian normalized GRIF is same for all density regions. And second experiment is comparing accuracy and consistency trade-off of GRIF, that is post-processing, and SEN-SEI, that is in-processing. In addition, the works algorithm cannot apply to this experiment because of poor scalability, because this data set is too large, having a large dimension, I mean. They use dataset name, bias, and toxicity. In bias, we need to predict the occupation of a person based on their textual biography, and prediction is consistent when it is same after swapping gender pronouns and names. In toxicity, we need to identify which is toxic comment, and prediction is consistent when it is same for all identities. And this identity is comment who write the comments. The experiment 2's result is left graph is trade-off of graph of bias and right is graph of toxicity. GRIF unnormalized is represented as orange line like this, and GRIF normalized is green line, and SEN-SEI, that is in processing, is red line. In both datasets, GRIF has more better trade-off than SEN-SEI. And there are no difference in GRIF and normalized GRIF in accuracy consistency trade-off. So thank you for listening my reviewing paper, and this is end of presentation. Thank you.